Today, we'll explore the concept of hexagonal architecture and how it can help us to create well-structured and maintainable software applications. We'll cover the core principles of hexagonal architecture, its benefits, and walk through a practical example to solidify our understanding. The main idea of hexagonal architecture is to separate the business logic from the outside world. All the business logic lives inside the application, while any external entities are located outside of the application. The inside of the application should be unaware of outside. Let's dive into the example. So, the goal is that the application can be controlled equally by users, other programs, or tests, right? And we should be able to develop and test the business logic in isolation from the framework and databases or external services. So, to make the separation of business logic and outside world happen, the application only communicates with outside world through ports. These ports describe the purpose of conversation between two sides. It's irrelevant to the application what technical details are behind these ports. Adapters provide connection to the outside world. They translate the signals of the outside world to a form understood by the application. The adapter only communicates with the application through port. Any port could have multiple adapters behind it. The adapters are interchangeable on both sides without having to touch the business logic. This makes it easy to grow the solution to use new interfaces or technologies. For example, in coffee shop, there could be some point of sale UI which handles taking orders for coffee. When an employee submits an order, a REST adapter takes HTTPS post request and translates it into the form understood by a port. Calling the port triggers the business logic related to placing orders inside the application. The application itself doesn't know that it's being operated through the REST API. On the other side of the application communicates with a port that allows persisting orders. If you wanted to use a relational database as a persistence solution, a database adapter would implement the connection to the database. The adapter takes the information coming from the port and translates into SQL for storing the orders in database. The application itself is unaware of how this is implemented or what technologies the implementation uses. As we have seen, some adapters invoke use cases of the application, while some others react to actions triggered by the application. The adapters that control the application are called primary or driving adapters, usually drawn on the left side of the diagram. The adapters that are controlled by the application, called secondary driven adapters, usually drawn on the right side of the diagram. The distinction between primary and secondary is based on who triggered the conversation. This relates to idea from use cases of primary actors and secondary actors. A primary actor is an actor who performs one of the application functions. This makes the port of the application a natural fit for describing use cases of the application. A secondary actor is someone whose application gets answers from or notifies. This leads to secondary ports having two rough categories: repositories and recipients. We should write use cases at the application boundary. A use case should not contain any detailed knowledge of technologies outside the application. Hexagonal architecture can encourage the preferred way of writing use cases. A typical mistake is that we write the use cases with knowledge about particular technologies. Such use cases are not speaking business language, become coupled with technologies used, and are harder to maintain. One goal of hexagonal architecture mentioned was the ability to test business logic in isolation from external tools and technologies. This is something that comes naturally from separation of concerns implemented with ports and adapters. Without the separation, or options for testing are much more limited, and there is a tendency for broader tests. The first step in implementing a use case would be to start with a test describing it. We begin with application as a black box and allow the test only to call the application through its ports. We should also replace any secondary adapters with mock adapters. While it's possible to use a mock framework here, writing your own mocks or stubs will prove valuable later. For any repository adapters, these mocks could be anything as simple as map of values. Integration test could make some HTTP request to the REST controller and assert that the responses matches our expectations. Although REST controller is calling the application is not the subject under test. If we use test doubles for application in these tests, we'll have to focus more on verifying interactions between the adapter and the application. When we only mock the right side adapters, we can focus on state-based testing, and we should make sure to only test the responsibilities of the controller in these tests. We can test the use cases of application on their own. When it's time to implement the right side adapters, you want to test that the integration of the third-party technology works correctly. Instead of connecting to the remote database or service, we can containerize the database or service and configure the subject under the test to connect to that. For example, we can use Docker. This allows us to use the underlying technology locally without having to rely on the availability of external services. Although we can cover the different parts of the system with unit and integration tests, it's not enough to weed out all problems. This is when end-to-end tests, also known as broad integration tests or system tests, come in handy. We can still isolate the system from external services, but test the system as a whole. These end-to-end tests execute entire slices of the system from primary adapters to the application to the secondary adapters. What we are looking for in this test is executing the main path of the application. The intent is not to verify the functional use case, but that we wired the application together correctly and it's working. This approach will eventually lead to some overlapping tests. To avoid testing the same thing on different level repeatedly, it's important to think about the responsibilities of subject under test. In conclusion, here are benefits of hexagonal architecture. Maintainability. By isolating the core business logic from external dependencies, changes to those dependencies have minimal impact on the core. This means you can update, replace, or add new external systems without rewriting large portions of your application. The stability. Hexagonal architecture promotes unit testing by allowing you to easily substitute real implementations with mock objects or test doubles. This isolation of the core logic simplifies testing and ensures that changes in one part of application don't inadvertently affect other parts. Adaptability. As your application evolves, new features may require interactions with different databases, APIs, or user interfaces. Hexagonal architecture makes it easier to adapt to these changes since the core remains untouched, and you can simply develop new adapters to integrate with the new technologies. Hexagonal architecture is guided by several core principles. One of them is separation of concerns. The architecture separates the business logic from concerns like database, user interfaces, and external services. The separation enhances modularity and simplifies maintenance. Dependency inversion. Traditional architecture often have the core dependent on external systems. In hexagonal architecture, the dependency flow is inverted. The core defines interfaces and The adapters implement these interfaces, leading to looser coupling. Flexibility. The modular nature of hexagonal architecture allows you to swap out or add new adapters without altering the core logic. The flexibility is essential in rapid changing software landscape.